Hi, my name is Zhong Wang. I'm a computational biologist. I work for the DOE Joint Genome Institute.
Hi, my name is Yue Li. I'm a co-founder, CTO of Memverge, a Bay Area startup focusing on big memory computing.
In this talk, Yue and I will share a recent study we collaborated on using precision memory as an effective alternative to random access memory in metagenome assembly. I will give a brief introduction to the background of this study, and Yue will then discuss what this study found. Here's a typical day of my life when I do metagenome assembly. After praying a week from a large assembly project finish, Metaspace crashes, auto memory again. Does this sound familiar to you too? Even if you don't do metagenome assembly, the OOM can still frustrate you in many genomics and computational biology projects. The rapid growth of genomics data is only going to make OOM more frequent. I did plot on the growth of genomics data in NCBI's short-read archive since the beginning of the next generation sequence era. It grows exponentially at a rate faster than Moore's law. It slows down in recent years, but still exponentially. JJ alone generates 450 terabytes of data in FY 2021, most from plants and environmental samples. Not only the total data volume increases exponentially, data from single projects are also getting monstrous. Here's a small subset of JGI's recent terabyte scale metagenome projects. I'm not going to discuss any of these projects. I just want to stress on that to get a deeper understanding of complex microbiome environments. People are sequencing deeper and deeper, again, getting more data. It's challenging to assemble terabyte scale metagenome projects. Metagenome assembly is a memory-intensive process. For terabyte scale metagenome projects, we have to think about scalable strategies to avoid OOM. We could simply add more RAM to a shared memory, single computer system, or we could use a node with bigger memory on the cloud. This is not hard. We don't have to change the code in the assembly software. Only offers limited scalability and limited performance though, as most big memory servers can only host a few terabytes of RAM and a limited number of computing cores. Another strategy is to develop assembler that can use distributed memory on the compute cluster or even on the supercomputing with thousands of nodes to achieve big memory capacity and faster computing. Develop this kind of assemblers are hard. It takes a team of software engineer years of work. Third strategy is to develop new algorithms to reduce memory and computer usage and increase the scalability. There are many metagenome assemblers, but few can assemble terabyte scale projects. Here is a list of 3 most common assemblers, all based on different graph. They each use a combination of some strategies we mentioned in the previous studies to achieve scalability. Metaspace and Metagenome take advantage of big shared memory, while Metagenome can use both shared memory and distributed memory architectures. People have built big shared memory and distributed memory systems. Only problem is they cost millions to billions of dollars to build. Most people don't have access to one. Next, I believe Yue is going to propose an affordable alternative.
Thanks, Zhong, for the introduction. In this work, we will focus on persistent memory, or PMEM. So PMEM is one of the most promising candidates that serve as a low-cost alternative to expensive DRAM. Persistent memory was first introduced by Intel as shown in the picture below. It offers large capacity per memory DIMM. They only cost a fraction of DRAM, and the memory is also persistent, meaning that the data persisted in such memory can be recovered after power failure. However, PMEM is slightly slower than conventional DRAM. Therefore, the best way to leverage persistent memory requires placing in memory data into the right type of the memory such that memory cost could be reduced without losing too much performance. In this work, we solved this challenge by implementing a memory tiering system that combines DRAM and PMEM into a single memory pool and provides very flexible performance cost trade-offs. The system is totally transparent to user applications and does not require any application modification. It offered a tiered memory consisting of DRAM as fast tier and PMEM as slow tier. The total capacity thus equals to the sum of the DRAM and PMEM capacities. After allocating memory to applications, our system further monitors the application's memory access patterns and will try to move hard data into DRAM tier for best performance and move cold data into PMEM tier for saving costs. To achieve various trade-offs between performance and cost, we allow users to configure different DRAM PMAM ratio for individual applications. The ratio can also be dynamically adjusted and even auto-tunable with our auto-tuning algorithms. For instance, users can make their performance critical application to run only in DRAM or using a higher DRAM PMAM ratio. And if one user wants to save cost, application can run fully on PMAM or use a very low DRAM PMAM ratio. Memory tiering is able to reduce memory cost significantly. This figure shows the memory cost saving calculated based on the latest server pricing from Dell. For instance, in a 1/4 DRAM PMAM ratio, memory cost is actually reduced by more than 100%. To see how well memory tiering can work for metagenome assemblers, we perform experimental evaluations on 3 popular metagenome assemblers, namely Metaspace, MegaHit, and MetaHitmer. We use the commodity Linux server that carries 768 GB DRAM and 6 TB persistent memory. The memory tiering function is freely available through our memory machine software. All the assemblers are evaluated against the wastewater metagenome dataset from NCBI, where we measured memory consumptions and execution time with different DRAM PMAM ratios. Here is a sample result for Metaspace. We plot the performance degradation and PMM usage as a function of PMM DRAM ratio. So the results show that when more and more DRAM gets replaced with PMM, the performance starts decreasing as expected. When the workload is fully running on PMM, Metaspace can still finish successfully, but becomes up to 2.2x slower compared to the running on DRAM. Here's another sample result that compares all 3 assemblers together. All 3 assemblers could successfully finish within a reasonable amount of time when running fully on persistent memory. MetaHitmer seems to be taking an extreme trade-off point where it takes the least amount of time to run, but consumes the greatest amount of memory. In conclusion, our experiment result shows that it is feasible to run a large-scale metagenome assembly on commodity hardware by substituting DRAM with persistent memory. If a running time is not a critical factor, persistent memory could be a cost-effective option to extend the scalability of metagenome assemblers without requiring software refactoring. Persistent memory may also scale similar memory-intensive bioinformatics solutions. Therefore, we think that persistent memory is a great candidate for memory cost saving. And also, as a joke, brace yourself, out of memory killers is coming. Finally, we would like to acknowledge our colleagues and friends from JGI, Memverge, and Intel for their help and contribution. Jingchao Sun from Memverge did most of the experimental work presented in this talk. If you have any questions or have similar big memory challenges with your workloads, please feel free to contact us using the email below. Thank you.